This is the last lesson for Chapter 4. We're going to be solving systems of linear inequalities. So you've probably graphed linear inequalities before. Now we're just going to talk about systems, which is very similar to a system of equations. Now a system of linear inequalities is just two or more linear inequalities and two or more variables. So I would like you guys to pause and make sure you copy this stuff down. You can check with the key too. But basically, you're solving very similar to what we did in a system of equation. Now the solution, though, of a system of inequalities is not just one point, it's any point. So it can be lots and lots it's actually an infinite number of points that satisfies each inequality in the system. Now to tell what satisfies the inequality, you're going to graph the system and then show what's called the feasible region, which shows every single point that satisfies the inequality, the systems of inequalities. Okay, now I'm going to do an example here with you, and then it'll start to make sense what this idea of the feasible region means. To begin graphing the first problem here, I'm going to do this one in blue. I'm going to graph just like normal, almost like it was y equals. So I start down at -5, and I'm going to do a slope down 3 to the right 4, or up 3, left 4. Okay, now the only difference is with an inequality is that I do not graph a solid line. I have to look and see the inequality here, which is a less than symbol. Since it's a less than symbol, or if it was a greater than symbol, it would be a dashed line. Okay, this represents that points on the line do not actually satisfy this inequality. So that means a point like here is not going to satisfy, so does not satisfy the inequality. Meaning if I plugged in the coordinate, let's say one that actually went through at 4, -8. If I plug that coordinate in for x and for y here, I would get a false statement because that does not satisfy the actual beginning inequality. All right, now I'm also going to shade here, and I'm going to shade below. This is a less than symbol. For a less than symbol, we're going to shade below the line. Now, you probably have also picked test points. I just want you to be able to do this kind of quickly. You can verify with a test point. A lot of times people pick the point 0, 0, plug that in and see if it's a true statement or not. So if I plug in 0, let me erase here. If I plug 0, 0, this coordinate here, into the original equality, I get 0 is less than 0 minus 5. I get 0 is less than -5. This is false, right? Which means we do not shade on the side with that point. We shade on the opposite side of this line down here. Now that's something I want you to be able to do really quickly. So, like I said, we would shade, this is a less than symbol. For a less than symbol, we want to shade below the line. Now sometimes people have a hard time with understanding what's below and above the line. Think of your skier. And we talked about the skier when we had a slope. This is a negative slope, first of all. But the skier, in order to be walking on this line, or skiing on this this mountain, let's call it a mountain, he has to be on this side, which is above the line. If he were on this side, he would just fall. You know, he's really underground. So we're going to shade below the line, so the opposite side of where that skier is. All right, now that's just graphing the first one. Now on the second question, I'm going to do this one, or the second line here. I'm going to do this one in red. And I'm going to graph using intercepts because it's in standard form. So I have an x-intercept at -6 back here, and a y-intercept at 2. And I'm going to graph this with a solid line. So if it's a less than or equal to or a greater than or equal to, we have a solid line as opposed to a dashed line. So now I connect those points here like so. All right, now for this question, think of if you were to isolate the y here. If I were to isolate this y, I would have a less than symbol still. I would not have to flip the sign if there was a negative in front of that 6. Then I would have to flip the sign if I were trying to isolate the y and put it into slope-intercept form. So again, I am going to be shading below the line. So if I were to shade below this line here, I would have, the graph would look like this. Now what I'm looking for is where these two parts intersect. So I want to graph only this section and shade this section here. Notice how these are where those two parts overlap. Okay, so I'm going to erase the red and the blue from this side up here, because technically this blue line keeps going forever in this direction here. But I'm going to erase here and here Whoops, didn't mean to erase the line. Let's do it again. Okay, so this is called the feasible region. Now your feasible region does not end here. Okay, it's not like it just cut off here. This is going infinitely. This is going to extend, and this goes forever and forever. But basically, any point that I now pick inside this feasible region has to satisfy these two inequalities at the exact same time. So let's say I pick the point -6, -3 right here. If I plug in -6, -3 into this line and into this line, I will get true statements for both. It satisfies both inequalities. Okay? So I also want to mention that feasible region means possible, right? The word feasible, like if you were to say that's not feasible, you were trying to say that that's not possible. So really what feasible region means is all the possible solutions to this inequality. It shows you graphically all the possible solutions, because it'd be impossible to list them all. You know, obviously there's an infinite number, so it'd be impossible to list all of the possible solutions. So you just show it with using a graph. All right, let's try number 2 now. So number 2 looks a little bit strange, but we know we can graph both of these using intercepts. So if I pretend like 0 is here, and I cover that up, if I'm going to solve this equation here, x over 4 is equal to 2, I just multiply by 4 to get an x-intercept of 8. So I'm going to graph 8. So I'll do the first line. Let's do it in green. So I graph 8, 0, and for the y-intercept here, I'm going to graph 4, 0, 4. Now when I graph this line, I'm going to do it solid, because that's a less than or equal to symbol, so I will have a solid line here. And I'm going to shade below. Now if I were to try to isolate this y, I'd only have to move this over to the other side, which doesn't flip the sign at all, so this is going to be a less than or equal to. Remember, less than or equal to, greater than or equal to, less than or equal to or less than symbol, you're going to shade below the line. For a greater than or equal to or greater than symbol, you'll shade above the line. And again, if I was imagining a skier here, like this, I would shade below here. I'm just going to draw little hairs this time so I don't have to go back and erase a bunch of stuff, especially since you're going to be doing it with pencil and you can't erase as easily as me. Just draw these little hairs in here showing that you're shading below the line there in that direction. Now in the second line here, to find the intercepts, let's do this in red. I do the same thing, so I get an x-intercept at +3, oops, not 2, and a y-intercept at -3. And when I graph this one, this will be a dashed line. And again, I'm going to shade here. I don't need to flip the sign. Since it's a greater than symbol, I'm going to shade above the line. So if you're imagining your skier here, you know, he's walking on this side. This is the above ground part. So you're going to shade here above, like so. All right, now when we look at where they overlap, I can see that I have green here and red here, which means that in this portion of the graph, these two lines will overlap, or the regions here will overlap. So let me connect this, keep going a little bit further. So this is what I want to see as my feasible region here graphed, and you're just going to use your pencil and kind of shade it in. So there's my feasible region. So just like a system of equations, a system of linear inequalities can have more than just 2 lines here. So I would like you guys to practice on this one and try to graph these. I'm going to graph that, pause, and then show you what the solution is. And then we're going to answer these questions over here because I think these are good thinking questions here. Graphing my first line, this is a line y equals 3. I have a solid line, horizontal line, and I shade underneath the line. My second line that I'm doing in blue is going to have a dashed line. So I started at 1, I went down 1 to the right, 3 for my slope, and I'm shading above this line, so that's where you're seeing the blue hairs here above the line. And finally, when I graph this one in green here, I have a solid line, and I'm shading below the line here. Now when you look and see where the intersection of these 3 overlapping regions are, it actually forms a little triangle here, inside here. Let me shade it in highlighter yellow here, right inside here. Okay. That would be just the feasible region. If I was just answering a question, you know, what's the feasible region, you just show this graph. But right to the right here, I have determine if the following points are solutions to the system of inequalities. So this is just making sure that you understand the idea of what a solution is not, and what it means to be a shaded or, a solid or a dashed line. So let's look at the point 17. Well, the point 17 is clearly not within that shaded region here, so this is not a solution. And if we look at 3, 0, 3, 0 is on the boundary of the shaded region. Now, normally I would say yes, that this would be a solution because it does fall on a solid line. However, it also passes through a dashed line. Because it passes through a dashed line, it does not satisfy every single line in this system here. So this is not a solution as well. If I look at negative 1, 3, so negative 1, 3 lies on the line y is less than or equal to 3. This is a solid line. So yes, this is a solution. Okay, so there's a subtle difference between when it's not and when it is. Sometimes it's very obvious because it does not lie at all within the shaded region, and other times it's going to fall right on a boundary line. And a boundary line just means where it splits the graph. Like this is considered a boundary line, so is this, and so is this, because it's splitting your graph into two parts. Parts that's shaded, part that's not shaded. Okay? All right, now on the back side, we're going to work a little bit backwards here. Now I'm given a graph, and I have to come up with the actual solution or system for this, this particular graph. So I have to look at each line and try to write the equation of each line. Now I'm going to start with, let's do the horizontal line here. This is a horizontal line, so we know that it's going to be a y equals line. Now it's a solid line, which means that we're going to select either one of these types of signs, the greater than or equal to or the less than or equal to. But when I look at the graph, notice how it's shaded above that line, right? It's shaded above the line here, the overall solution. So I'm going to pick the greater than or equal to symbol. So this line is y is greater than or equal to, and it goes through the point 3, so it's y is greater than or equal to 3. Now working on this line here, this is a dashed line, which means right away I know I'm either going to select less than or greater than. Okay, so I have y, and in this case, notice how it's shaded above the line. This would be shaded above this line, so we're going to pick again greater than. So y is greater than, and then let's work on the slope and the y-intercept here. So the y-intercept here goes through 1, the slope goes up 1 and it runs, or sorry, goes up 2 and runs 1. So that would be 2 over 1, or just 2x plus 1. And that's the system here that shows this graph. So this is the feasible region. If I were to graph, I would get that section here. I would like you guys, actually I'm going to do 2 with you, and then I'm going to have you guys try 3 and 4 on your own and check with the key. The only thing I have to do in number 2, because this is a new type of line here, is this the vertical line here. Now hopefully you know that this is going to be an x equals a number. So we have x and then it goes through 2. So it's going to be either, it's a dashed line, a less than or a greater than symbol. Now some students get really confused here because they're not sure which symbol it should be. Now think about it this way. If I were to ask you to graph on this line here, it's going to split values that are less than 2 or greater than 2. If I were to shade on this side, I'm showing all the possible values that are less than this boundary, this 2 value here. So in this case, since I see that it's shaded to the left here, this is going to be a less than symbol. This shows all values that are less than 2. If I wanted to show values that are greater than this line 2, right, this is the boundary line for 2, I would be on this side of that line here, and that would be a greater than 2. So anyways, coming back to the original graph here, since it's shaded to the left of that line, it's a less than symbol. And it's also a less than symbol because it is dashed, right? We don't see a solid line. And then the other line here is a y equals line, and in this case, it's shaded below that line, and it's solid, so I'm going to do less than or equal to, and that number is 4. So for problems 3 and 4, I would like you guys to try these. Remember that you're going to have, you can have more than 2 lines, and in this case you see 3, right? We see 1, 2, 3 different lines. So you should have 3 lines for each of these systems. Make sure you just go through step by step, picking the correct sign, and it should be very straightforward. Okay. All right, the last problem on this note sheet is an application problem for this system of linear inequalities. So take a second to read the actual problem, and then we'll go through it together. Alright, so you're taking a test, and you've got 2 types of questions, type A questions that are worth less than type B questions. For each type of question, it takes a different amount of time to complete also. One might be harder than the other. And you have a total number of, or total time allowed. And you're also, I want to change this, sorry, it's a typo here. It says you may answer more than 16 questions. I want to make it no more than 16 questions, okay? All right, so let's define our variables. We have two different types of questions, and those are the two variables that we're going to use because we don't know how many questions we're answering of each type. So I'm going to write x is equal to the number of type A questions, and y is equal to the number of type B questions. Now, there's also extra information in this question that makes it trickier, I think, for you because you have to discern that this is just extra information. The only two things that you have a constraint on, a time constraint on, or a constraint in the number of questions that you can answer is the 60 minutes and the fact that you can't answer more than 16 questions. Now, the fact that it's worth 10 points and 15 points has no bearing on whether, the time or the number of questions that you can use. So this part of the sentence here is totally meaningless. So you want to focus on only the information that is important to your particular problem. Now, it says that you can answer no more than 16 questions, and this is where your very basic inequality is going to come from. If I take the number of type A questions and I add to that the number of type B questions, so the total number of questions that I'm able to answer, that cannot be any more than 16 questions. So no more than 16 questions means that it must be less than or equal to 16. So you have to think about these types of things the way it's worded. A lot of students will see the word more and they want to do a greater than symbol. So just be really careful about that. Make sure that it makes sense in the original problem. Pick a couple numbers and talk about whether or not you can answer up to 16 or more than 16 or whatever. Just make sure that you have this symbol correct, okay? So the reason why I'm picking a less than or equal to is because I can answer 16, but I cannot answer anything more than 16, which means I can't answer 17 here. So that's why it's less than or equal to the 16. Now the second inequality is going to come from the fact that it takes 3 minutes per type A question and 6 minutes for type B question. So if I take 3 minutes for every type A question and I take 6 minutes for every type B question, so that's literally what I'm saying out loud is what that would mean, this 3x plus 6y. 3 minutes per type A and 6 minutes per type B question here. Then I have a total of 60 minutes to take this test. So this is going to be less than or equal to 60. Okay, that's the system here that I'm going to use, and I'm going to graph this on the grid here that's provided, and then I'm going to state the combinations of A and B that would comply with the above constraints. So basically this last part here is very similar to what we did on the front page where we decided whether or not something was a solution to the system. All right. Now when you look at this doesn't have a 20 by 20 grid, so I'm going to have to scale this down a little bit, but my X and my Y intercepts in the first question only are 16 and 16, right? So I need to be able to show 16 and 16, 0, 16, 16, 0. But in the bottom one, people see this 60 and they think that their scale has to go all the way up to 60. It does not, because if you think about it, if I were to actually solve for the intercept here, I have an intercept at 20, 0, and one at 0, 10. Okay, so really, I need to just go up to 20 in the X direction, and I'll probably do the same for the Y direction as well, even though I don't need to go all the way up to 20, because I only need to really go up to 0, 16. Okay, so that's how I'm going to determine my scale here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So I'm going to let each of these represent 2. So all the way over here is 20, and halfway in between 2, 4, 6, 8, 10. This is 10 questions. 2, 4, 6, 8, 10, and 20 up here. Let's label. So this is going to be the type A questions. So this is number of type A questions. And then this is going to be the number of type B questions. All right, if I graph x plus y is less than or equal to 16, then I have a point on 16, 0, and one at 0, 16. I have a solid line for this, and I will shade below. Now, make sure that you're using a ruler so that you can get it as accurate as possible. Obviously, I can't use a ruler on top of my computer, but you want to make sure that you're using a ruler to make this as accurate as possible. The next inequality here, let's do this one in blue. I have an intercept at 20, 0. So I'm going to go to 20, 0 here. And I have one at 0, 10. So go to the 10 here. And this is also going to be a solid line shaded below. So if I graph my feasible region here, notice how both of these are shaded below. Then that means that it's going to be in this region where they overlap. throughout here. So let me do this in yellow. You're going to have nice crisp lines because you have a ruler. But basically, this is the boundary line here intersecting with this here, and it's forming a quadrilateral. It's a four-sided figure. And the reason why this does not continue down here is because this is a real-world problem, right? You can't have a negative number of questions, so that's why we're only looking in the first quadrant. This is the first quadrant. It's all positives, you know, positive x values, positive y values. Okay, so that would be the feasible region. Now, to answer part C here, state 3 combinations for A and B questions that would comply with the above constraints. Well, if you wanted to, you could answer all the way down here. This is on, this point here is on the boundary line, and it's on a solid line, so I could answer 16, since 16, 0 is on the line, right? I can answer 16 type A questions and 0 type B questions. Okay. I can also answer this top line here, or this top boundary point, 0, 10. That would be meaning 0 type A's and 10 type B's. So I don't have to answer a total of 16. I can't answer more than 16. Okay. Now, a third point, I could pick where those 2 points intersect, and that's actually what we're going to start talking about in the next chapter. I'd have to find the intersection of these 2 points, and hopefully some of you guys are realizing that that's just simply a system of equations that you're going to solve for, but we're kind of getting ahead of ourselves. We don't have to find that point. And then obviously anything inside here, you know, works as a coordinate. I don't want to pick something like 2.1 though, because I can't answer 2.1 questions. So make sure that these would be integer values, since you're dealing with a real world problem. But basically you can list lots and lots. I can do 8 and 2, right? 8 comma 2 here would be in that feasible region. And you would just basically be, the skill here is just making sure that you can interpret what those mean. So this is the number of type A questions, this is the number of type B questions, and so on. Okay? Alright, that's the end of the lesson. Thanks for sticking in there for 23 minutes or so. Make sure you come to class ready to graph and to be able to tell me what these two types of, or what these two systems are. Okay, please make sure you're practicing this just to get the practice and make sure you know how to do it. Alright, I'll see you tomorrow.